Okay, so this is a brief set of notes on the limits and continuity of vector valued functions. Okay, so we have to define a limit, right? So a limit of a VVF, vector valued function. Alright, so we're going to let R of t be a vector valued function. Is a VVF. Okay, so we're going to define the limit as x approaches a of R of t. Well, we're going to assume that this function contains f of t, g of t, h of t, and we just do it component-wise. So this is going to be the limit as x approaches a of f of t, and the limit as x approaches a of g of t, and the limit as x approaches a of h of t. And this simple component-wise definition, in fact, actually just does everything that we need it to do, so this is the one that we go with. There's one little small caveat here. This is provided all limits exist. So if for some reason one of these three limits doesn't exist, then this limit doesn't exist either. So that's a small little parenthetical remark, but the limit is this if the limits exist. Now, the nice thing about this is we don't have to break back to all of that for every epsilon greater than 0, that kind of stuff that we did in BC Calc. It's just a matter of we can use the typical definition of a limit that we established back then and just kind of grow on that. One of the nice side effects of this is that the definition of continuity follows the same. So if I have the continuity of a vector valued function, again, we let R be a vector valued function, and we just actually build off of the idea of continuity when we have regular ordinary functions. So if the limit as t approaches a of the vector valued function of R of t is equal to that function at a, then we say R is continuous at t equals a. Okay, so pretty simple idea. And if it's continuous at all t's, then we say that it's a continuous vector valued function, so forth and so on. There's no great mysteries here. So continuity is basically the same thing. Remember, these things are like plotting as curves still, but they're like curves in space. So if they're nice and neat and keep going along, then we have a continuous curve, right? So something that would have a discontinuity might have a hole inside the curve, or you might have a curve that's coming along and all of a sudden it juts off to something and then comes back, and these limits aren't equal, right? Got to actually have some sort of asymptote there, right? And then the curve keeps going. We have a similar reality that we would in 2 space. It's just a matter of continuing this into 3 space. Okay, so that's it. Limits are limits, continuity are continuity, and it all works component-wise.